Welcome to qnawire.
Hi everyone, so what we have is steam expanding in a turbine steadily. We know that there is some work that is outputted, and we also know that there is some heat that is lost. So what we're asked to find is the mass flow rate of steam through this turbine, the exit velocity of the steam, and the power output given certain parameters. So first what we're going to do is go through our assumptions. So we know that this is operating at steady state, so conditions will not be changing with time. And we're also going to assume that any changes in potential energy are negligible. Next, what we can do is, using the states that are given to us, we can determine some parameters. So we know the input pressure is 7 MPa and input temperature is 600 degrees Celsius. Using this information, we can use the steam tables to discern that our specific volume at our input is 0.05567 cubic meters per kilogram, and our incoming enthalpy is equal to 3,650.6 kilojoules per kilogram. Similarly, we can use our exit state that's given to us. We know the exit pressure is equal to 25 kPa, and our exit quality is equal to 0.95. Now, utilizing those same steam tables, we can discern that our specific volume at our exit is equal to 5.8933 cubic meters per kilogram, and our exiting enthalpy is equal to 2,500 kilojoules per kilogram. Next, we can solve for our mass flow rate going through the turbine. So recall that mass flow rate is equal to rho times velocity times area. And rho can be rewritten as 1 over specific volume. So we can rewrite this as 1 over specific volume, velocity times A. Now at state 1, we know all of these quantities, so we can go ahead and calculate our m dot, and that's going to be equal to 16.17 kilograms per second. And that is equal to our mass flow rate. So that's one part of our answer. Now, since we are operating at steady state conditions and there's only one inlet and one exit, this mass flow rate is also our exit mass flow rate. So we can use this to determine our exit velocity. So m dot is going to be equal to 1 over v velocity times area, and we can just go ahead and put in subscripts here to designate we're looking at the exit. So solving for our exit velocity, we see that exit velocity is equal to m dot specific volume 2 all over area 2. We have all this information, so we can go ahead and compute velocity at 2 to be equal to 680.6 meters per second. And that's another part of our answer. Lastly, we're asked to solve for the power output of this turbine. So what we can do is go ahead and do an energy balance and say that the energy coming in minus the energy leaving the system is equal to the total change in energy of the system. Now, we are operating at steady state conditions, so the total change in energy of the system is equal to 0. Therefore, the energy coming in is equal to the energy leaving. Now we can go ahead and break this part into its constituents and say that the energy coming in is equal to m dot h1 plus v1 squared all over 2, and the energy leaving will be the power plus also the heat that we lose plus m dot h2 plus v2 squared all over 2. Now we can go ahead and isolate the work and say that work equals negative q dot minus m dot h2 minus m1 plus v2 squared minus v1 squared all over 2. And plugging in for all these quantities, we get in power output equal to 14,560 kilowatts. And that's our final answer.